Okay. Uh, dear colleagues, we are about to start our fourth working day of the conference. So the first speaker of the first session of the fourth day is Vladimir Turaev, and he is going to tell us about knots and links in two-dimensional complexes. Let's welcome.
All right, so knots and links in two complexes. On one hand, it sounds very strange because we all know knots and links in manifolds of any dimension and of any codimension. In particular, here we focus on one-dimensional links and knots in three-dimensional manifolds. But let's come back to the origin and to the knots and links in the three-dimensional sphere. We all know that knots and links can be drawn on the plane, on the two-dimensional sphere.
Sorry to interrupt, but are you planning to share slides? Right now, we don't have anything on our screens.
No, nothing at all.
Okay, thank you.
Can you see me?
Yes, yes, we can see you. Thank you.
All right, I'm planning to share my paper on this subject. Let's see if I manage to do it. Yes. I'm going to share. Why to do slides if I have a paper?
Yes,
right.
We can see that. Thank you.
So we can see, we know that there are knots in R3. They are usually drawn by pictures on the plane, and there are randomized moves. And in principle, this fully describes the theory of knots and links in R3. Just pictures on the plane or on the two-sphere and the randomized move. Now this actually doesn't need the three-dimensional space. It's enough to have the sphere, some pictures on the sphere, some moves from those pictures, and that's equivalent to the usual knot theory. It is not very spectacular because you don't see many things. For example, cobordisms in four space or even Seifert surfaces, we don't see them, but still we can see many things. Now, the idea at the beginning of this paper was that we don't need three space. Let's try to draw similar pictures on any two-dimensional complex, not necessarily the sphere. So we take a two-dimensional complex, which may be, well, in my talk it is finite. And what is a knot on such a complex? How we draw knots? Well, we draw circles with nice generic intersections, one circle or several. Now, what to do in the crossings? Now, the usual method is to say that one overcrossing branch is higher than the second of the branches. Unfortunately, here in the two complexes, there is no notion of higher, lower, so we cannot use these ideas. So instead of using these ideas, I'm going to use a different way, different method, namely at every crossing, one pair of adjacent regions is distinguished, which is marked by dots. So we have two dots at every crossing. And now the disadvantage of this idea, of course, that you don't see it as nicely as in the usual way. On the other hand, it applies to arbitrary two complexes, which may be embeddable or not in three manifolds. So in principle, this theory of nodes applies to two complexes which are not even embeddable in three-dimensional manifolds. So this enlarges our, well, the area. For example, one particular example is node and link diagram for the projective space, RP3. These are going to be pictures in the projective plane, RP2, with additional structure in the crossings. All right. Now, these are the standard basics, randomizer moves, not pictures. Now, what about those dots? Let's see the dots. Now, how we pass from the usual crossings to dots? Let's take the overcrossing, the usual pictures in the plane. Let's take the overcrossing branch and rotate it counterclockwise. The first two regions that we meet are marked by dots. So that's what you see happens in figure 2. Now, do we preserve the information? Yes. If everything happens in the plane, then we can recover the original overcrossing and undercrossing just looking at those dots. So we don't lose any information, right? For example, here we have pictures of the left-handed trefoil and right-handed trefoil. These are non-standard pictures, but still they keep all the information which we need. Now the randomized moves can be rewritten in this language. You can see them. So that's the first randomized move. It has two versions. That's the second and the third randomized move. So you can see them, you can draw them in that way. And again, for diagram, not only diagrams in the plane, we don't lose any information. This is absolutely equivalent method. But the difference is that we don't need to have a plane. We can apply the same moves to similar pictures in an arbitrary two-dimensional complex. So that was the original idea of this paper. Now, the dot should be in the opposite regions. So at every crossing, there are two possible choices. So in principle, you don't even need two dots. It's enough to have one, because the opposite region at this crossing is automatically recovered. But just for the name of equilibrium, I'm going to use two dotted pictures. All right. Well, of course, similar methods apply to braids, tangles, and all the other standard mathematical tools. of this type. But I'm not going to talk about braids and tangles. Just let's focus on knots and links. Okay. Now here explains that everything is nice as possible. Graphs are finite, there are vertices, there are edges. Well, here we meet first examples of two-dimensional complexes. These are cylinders over graphs. So we take a graph multiplied by a unit segment that gives us a two-dimensional complex. We can also take a cone. Another method is just to take two vertices and connect them by edges, one vertex to the second vertex, and you take n parallel edges. So, for example, we get a circle in this way, a circle with a diameter, and so on and so on. Well, formal definition of a two-complex, there is nothing particular here. There are areas, two-dimensional areas, which are just surfaces themselves. There are edges. Now, near every edge, I assume that everything is nice. So every edge is adjacent to several areas or regions. And also there are vertices. Vertices are as nice as you can imagine. So near each vertex, the two-complex is a cone over a graph. So every vertex is adjacent to several regions and to several edges. Now, what are closed curves? Again, that is the most simple notion you can imagine. A closed curve, it's a curve, closed curve. Now, these symbols I use is interior of X. X is my two-dimensional complex. Interior of X means the union of all two-dimensional areas. So it's open to manifold. And this symbol read X, which I use, for example, in the first line, in section A, 3.3a, read X is the union of all edges. So you take all edges, don't include vertices. So all edges without vertices, and take the union. That's a one-dimensional manifold. So our closed curves, which represent knots, should lie in the union of those two, which means that they just avoid vertices. They lie everywhere they want, but not in vertices. Now, crossings are double transversal crossings, and they should lie in two-dimensional area, so it's the union of regions. Well, the point C, you don't have to look into that. This is simple to understand. Now, what happens when a curve wants to go from one region to an adjacent region? It has to cross. It has to cross an edge. And near this edge, near this crossing point, everything should be nice as possible. So we just meet this edge in one point, and directly go through one region to another region. Or maybe the same. The region may be attached to itself along several edges. All right, so there are some, here you have some examples. For example, all complex surfaces are two complexes without edges and without vertices. One for any graph, finite graph, the cylinder of the graph and the cone of this graph are two complexes in this sense. Now I fix this notation. Two complexes denoted by the letter X. And what are nodes and links? So a link is just a family, finite family of closed curves, which is, well, everything is generic. So crossings are just intersection points of two arcs. So locally it is a cross, but there should be dots. Dots are not supposed to have any geometric meaning. These are just formal additional data, and a pair of opposite dots should be chosen in every crossing. So that's in a sense a lift from curves to nodes. When there are dots, it means we have nodes, a node or a link. All right, there is a notion of mirror image. The mirror image is obtained by just switching our choice of dots at every crossing. If we switch the pair of dots, the chosen pair of dots in every crossing, it means that we pass from a link or a node to its mirror image. Now we can and should actually define the images, the Reidemeister moves, or the analogs of the Reidemeister moves. First of all, we have the dotted Reidemeister moves. We already saw them, and I'm not going to put them forward again. So these are the usual Reidemeister moves in the plane. Though instead of over under, we use those dots. Now, since if I wanted to talk about surfaces and nodes in surfaces, then I wouldn't need to speak about anything else, because the surface is everywhere two-dimensional, and it's enough to have those dotted Reidemeister moves. But since we deal with two-dimensional complexes, I need to explain what happens near the edges. Here, in those figures 5 and 6, the edges are represented by horizontal lines. So the horizontal lines are not parts of our knot, of our curve. These are edges. Every edge is adjacent to two or more regions. Here we see only two in these pictures, 5 and 6. The upper half plane and the lower half plane represent two of the regions adjacent to the given edge. So in the upper figure, you have part of our knot, of our curve, which crossed this edge in 2 points. And then the move consists of pulling this curve down, so it doesn't cross at this place. The crossings disappear. No, there are no dots, because edges and curves, the mutual intersections are not dotted. Now in the figure in the figure 6, you see what happens when a crossing, so you see a self-crossing of our link. The horizontal line again is an edge of our two complex. And what happens when the crossing point is pulled from one region to the adjacent region? Well, nothing happens. Basically, the crossing is preserved as is. So that's simple. This is the moves M5 and M6. Now, what happens near vertices of the complex? Now, that's more complicated, and I was not able to write to draw a picture. Now, the idea is very simple. It happens as little as possible. So, if your curve goes near vertex, near this vertex, our two complex is a cone over some graph. Well, the part of your knot here is a simple curve, so no self-intersections, and you can move it inside this cone in a way you want, in any way you want, without creating crossing points, new crossing points. Well, here it is discussed in more details, but I don't want to talk about it. It is not going to play any substantial role. Now there is one more move, that's move M6. It shows what can happen near an edge. Not only we can cross an edge, we can not only we can pull our diagram across an edge, but we can create additional crossings with the edge. So in my conventions, it is still a move on the nodes, write a master type, and basically the node doesn't change. We created an additional crossing with an edge from 1 to 2 or backwards, and the node is the same. Now the links are said to be isotopic if they can be transformed into each other by those moves and their inverses. Now, one important thing is that classical links in R3, can be drawn in our complex just locally. Take a region, a small piece of this region, and draw your link, but of course in the dotted way. No over-under crossings. So you get the link in the complex. Now, which region you choose? That's up to you. But if two regions are adjacent, you get the same nodes. So adjacent means that they meet along an edge. So you can push your picture from a region to an adjacent region, and so on and so on. So, for example, if your two complex is actually a surface, then you can reach, and your two complex is a triangulation of the surface. Then you can pull a picture to any place, of course, provided the surfaces connect. Now, what is the connection between these ideas and links in three manifolds? The connection is simple. Is our two complex is embedded in an oriented three manifold? It is important that it is oriented. So if a two complex lies in an oriented three manifold, then every link or node in these two complex determines a link in this oriented three manifold. Now, how it is done? It is done, well, the orientation is used to resolve the crossings. So in the picture of the node or link, we have crossings with those dots, and those dots plus orientation of the ambient manifold allows us to determine what is which branch goes to which side. So this is explained here. I don't want to go into these technical details, but why it is important? It is important because basically it means that nodes and links in oriented three manifold can be drawn in two-dimensional complexes without losing any information. Well, in the role of these complexes, you can, for example, take, for example, the two skeleton of a triangulation. So you take any triangulation, it's two skeleton, and then you can draw arbitrary knots and links in this manifold on this two-dimensional complex. You cannot draw above or under because you don't know which side is considered to be above or under. Of course, we could do it by orienting all simplexes, but that would be too complicated. And also the moment of crossing edges, when you pull a component across an edge, it's not quite clear what does it mean orientation is preserved, because adjacent regions don't have to have compatible orientation. So it's better not to deal with orientations and deal with dots. It is simpler. Also, instead of two skeletons of triangulations, one can use the dual two-dimensional complex. So we will have a triangulation. You take a triangulation, you consider the dual two complex, which is nice because all vertices are standard. At every vertex you have, every vertex is adjacent to just six regions. Every edge is adjacent to just three regions. So the whole theory simplifies considerably. But that's still a partial case of that construction. All right. Now what happens with surfaces? If we draw our dotted diagrams of surfaces, then every surface can be embedded, of course, if it is orientable. It embeds the surface cross the segment. If it is non-orientable, it embeds the zero section of the segment bundle over the surface. In this way, any dotted picture in the surface determines of a knot. Determines a knot so is a product of the surface with the segment, if it is the surface is oriented, or in this the total space of this segment part. In particular, when the surface is RP2, the projective plane, it embeds in RP3. And the normal bundle is one-dimensional bundle with segments as fibers. And so every picture in RP2 determines a dotted picture determines not a link in RP3. Of course, there is also a ball, so it is RP3 minus a ball, but the ball doesn't play much role here. So we get the same, we get a representation of knots and links in RP3 by pictures on the projective plane. Now here we have only 3 moves, M1, 2, 3, and the inverses, and that's it. And of course that's enough. As in Rademacher's theory, it is enough to represent isotopic classes of knots and links in RP3 in terms of dotted pictures on the projective plane. Well, now some strange things happen. Any two links, well, of course, we need to speak now about oriented links. Oriented means that each curve is individually directed in some direction, and the moves should preserve those directions. Now I define the linking number. So we take an arbitrary two-component link. So, well, it is, I'm talking about classical links, but we can do it in for arbitrary two-component oriented links in our arbitrary two-complex. So at each crossing we define +1 or -1, as in this picture, and take the sum. So the linking number is defined for arbitrary two-component links. Of course, it is symmetric, but we don't have any homological conditions. The components individually may be homologous to 0 or not, we just don't care. Now, what happens for local links? Links is drawn in small regions of our two-complex. What you get is twice the usual linking number. Well, here explain this. All these signs plus minus ones then sum up to the usual linking number multiplied by 2. Well, moreover, if you take just a knot, well, dotted knot, then it has a kind of framing. A framing, I call it rice. And there are two types of framing. One is unoriented, and the other is one is defined for unoriented links, unoriented knots, and the other defined for oriented knots. But neither of them are preserved under the first Rademacher move. So they are similar to what happens in R3. We don't get isotope invariance, and because of the first randomized removal. Well, here you have an example. A link in a Möbius band. That's the link which goes from the point A on the left to the point A on the right, sorry, A prime on the right, and A prime is glued back to A. So here we have two component links, A prime, and B prime. And the crossing, my choice here is indicated by the dots. Now the linking number is equal to 1, and the linking number of the mirror image of that link is equal to -1. Well, of course, you can draw many more pictures of this type. That's a two-component link in the annulus. Now, more invariants. Well, maybe I skip that part and that part and come to the bracket polynomial. So the bracket polynomial is defined for all links. So that's Lu's definition of the bracket polynomial. His classical definition of the classical bracket polynomial in R3, it applies in exactly the same way to links in arbitrary two complexes. We have here in the bottom of the picture, you see the standard, the standard formula. Well, there is some, the same coefficients. So basically, we take all possible ways to resolve crossings, so to remove crossings and smooth at all crossings. So C is the letter C here, capital C denotes a subset of the set of crossings. And in those crossings, we resolve the crossings so that the dots meet. The two dots at those crossings meet. And in all other crossings, we resolve so that locally the two dots don't meet, remain in different places. And then we sum up over all possible ways to choose this set C. So we get the bracket polynomial. So here you can see this possible smoothings, and there are coefficients. So we get we get a bracket polynomial which is not normalized. So it is not invariant, but we can normalize it using those rices which I described before, which are just of sums of all signs at all crossings. And then we get a normalized bracket polynomial, which is an isotopy invariant of our nodes. Now here, some results. Of course, at this point, one should stop and start thinking, not only reading. What can we do with this? First of all, what about other invariants? Can we extend other invariants or not? Well, that's interrogation sign. I did not try to do more. Now, can we extend other results? Here I extended one result. It estimates the number of crossing points of a link in terms of some of those invariants. Span is, of course, the span of the bracket polynomial. What is S? This is the middle invariant as C of L. it is the number of split components of the link. So a link is unsplittable if it is not a disjoint union, roughly speaking. So SC of L, it is roughly speaking a set of disjoint components. Disjoint means those that have no crossings. Well, for example, for knots, it is just one. So this number is of no interest for knots, but we still have a non-trivial estimate of the number of self-crossings of a knot in terms of the span of the bracket polynomial. So some things extend, some things don't extend. Now, what can we do more, which is not related to the... For this, we need to go back. And can we do any homotopy invariance of knots? The answer is yes. We can do at least some. What we can do is, for example, we take an arbitrary small crossing, whatever other dots, and smooth it, as in this picture 11. The smoothing is determined by orientations uniquely, so we don't use the dots. So this operation applies to oriented nodes or oriented links. So with the smooth at all crossings independently, we get lots of so let's see. Here we start with a two-component link, and we smooth at the crossings of different components. So for such crossings, after smoothing, we get just a knot. And if we forget the dots, we get a curve, and we take its free homotopy class. So the capital pi denotes a set of all free homotopy classes of loops in our surface, in our two complex. Now we sum up with signs, and the signs are determined by the dots in the way I described. So what we get is a link invariant. Well, this should be checked, but it's easy to check. That is a link invariance of this oriented two-component link. So I gave a name to this linking class of this link. Now, what is the interest here is that we combine the ideas of homotopy theory and the ideas of knot theory. Signs are determined by the knot information. Smoothing and homotopy classes are determined uniquely by homotopy information. Now, another construction of this type is a co-linking class. Namely, we start with an oriented knot in our two complex. Again, an arbitrary knot. We take an arbitrary self-crossing of this knot, C, and when we smooth this crossing, and there is a unique natural way of the smoothing, which is determined by the orientation of a knot. So we want to be smoothing orientation compatible. So there are two. When we do it at the crossing, we get a link in our complex, which is still oriented. Well, here I forget that it is a link. I just take the homotopy classes of the underlying loop. But the small problem we meet is that we have two loops and there is no natural order. So we need to consider both orders. So first and second. There are two ways to order this pair of loops. And then we define this co-linking number again in the tensor product of the free abelian group whose basis is a set of free homotopy classes, and we multiply it by itself. The knot information is in the sign of C. So this is plus or minus 1, depending on the dots. So that turns out to be a knot invariant. So under all those transformations of the knot, we still keep this expression. So I'm sure there are more potential ways to extend this theory, but that's the part which I wrote and which I enjoyed to expose. Well, I stop here. Thank you very much.
Okay, thank you very much. Are there any questions or comments?